Welcome back to the workshop. We want to continue taking a look at probability distributions, in particular, the cumulative probability function. Let's see here. Distribution function, the cumulative distribution. That's what we want to take a look at. All right, so let's take a look at our notes. We have a new theorem to take a look at for this video. So capital F is our cumulative distribution. So the values of the cumulative distribution, also called the distribution function for a discrete random variable, satisfies these two conditions again. So f of negative infinity is equal to 0 and f of infinity is equal to 1. Really, in both of these cases, you want to think of it as the limit as x goes to negative infinity of f of x, and the limit as x goes to positive infinity of f of x. This is much more appropriate notation. That's certainly what they mean when they say this sort of thing here. Now, I think a lot of the examples don't have an infinite number of values. For example, if we were to consider this, right, we can see that as we go to negative infinity, well, everything below 0 has probability 0. So we do have, in fact, capital F, the distribution function at negative infinity is 0. Excellent. And then the distribution function at infinity, so right, everything above our last value here is 1. Excellent. So that's kind of what we're saying here. As we look this way on the graph, it's 0. As we look this way on the graph, it's 1. That's what this is trying to say. Okay. So as we look at having none of the outcomes occur, the probability is 0. As we look at having all possible outcomes occur, the probability is 1. This is an impossible event. It is impossible for us to have no outcome from the sample space occur. This is a probability of 1. This is a certain event because this is saying what's the probability that we're going to have any one of the outcomes occur from the event? Well, of course, that's exactly what's going to happen. That's why it's an outcome in the sample space. Okay, so sample space rather here, but the probability of the sample space, anything from the sample space occurring, is 1. Yes, of course. The probability of nothing from the sample space occurring is 0. Of course. So those should make sense, right? The idea of those makes sense notationally, and now described as functions. This is how we can say that. All right. So the other thing that we need to observe is if we are creating our distribution function by adding values together, then as we add more values, we should get a larger function value. Of course, none of the things that we're adding together are negative because none of our probabilities are negative. All probabilities are between 0 and 1 inclusive. So we cannot take away, we can only add, we can only make it bigger. So as we increase our observable value, of course, the probability should increase as well because we're adding more probability to it. And that's all that this is saying. If A is less than B, then the cumulative distribution function should be less here than it is there. Okay, this is because we have a little bit and then it's a little bit higher, except it's a distribution function, not a histogram. So it increases to be 1. Okay, it's increasing. This is the definition here of a non-decreasing function or an increasing function, however you'd like to say that. But these things make sense to us, hopefully, in light of how the cumulative distribution function is defined. So let's take a look at an example. Just observe that these two conditions are satisfied. So this is a little bit interesting, kind of fun. Again, we're looking at a little bit more on the calculus side of things. So let's consider our previous example. This is our distribution function. Okay, this is our distribution function. We want to observe that it is a increasing function or an increasing function, and we want to observe what the limits are. One important thing to note here is that well here, for x less than 1, f of x is equal to 0. Okay, we have infinite values as we increase, but right, we can plug in 1, 2, 3, 4, 5, 6, 7, 8, and that continues on forever. But we can't plug anything in that's less than 1. So everything less than 1, we would say that the cumulative probability is 0. So the first thing is to look at this guy. So for number 1 here, f of negative infinity is equal to the limit as x goes to negative infinity of f of x. But, right, we're saying that this is the limit as x goes to negative infinity of 0, because for anything less than 0, when x is less than 0, the function value is 0. And of course, that's 0, exactly what we're looking for. And f of positive infinity is the limit as x goes to positive infinity of f of x. And in this case, we keep exactly the function definition, 2 to the x minus 1 divided by 2 to the x. And of course, maybe you want to use L'Hopital's rule here, or maybe you want to look at the ratios or whatever, lots of different ways to evaluate what this limit is. And actually, wow, something that I give my students a hard time about, hopefully you noticed it here, I accidentally left off the limit notation. So this is the limit as x goes to infinity of 2 to the x minus 1 divided by 2 to the x. Excellent. But of course, this is in fact equal to 1. So excellent, we have the first condition satisfied. Now, what about this condition, right? That it's non-decreasing or that it is increasing. Well, for this one, we want to take two generic numbers a and b. So for numbers a and b, where a is less than b, what we're going to do is we're going to let b be equal to a plus k. And of course, since b is larger, we have that k is greater than 0. This will help just simplify our writings here. Now, one thing that we can notice is, well, right, this isn't a continuous function, it is a discrete function, despite the graph being drawn in this way. So really what we're looking at is we're looking at a sequence. We're looking at a sequence of numbers. And this sequence of numbers we're saying should go, be increasing. So this is again reaching back into calculus 2. How can we show that a sequence is increasing? Well, we can, there's two ways to do it. Well, there's one good way. We can take the ratio of 2 of the elements, right? Two generic elements. Or a lot of times what we do is we take the kth element and the k plus 1 element. And we show that the ratio is either greater than 1 or less than 1, depending on what exactly you're looking at there. So to show that it's increasing, let's see here. So to show increasing, we want to show that f of, let's see, how did I put it here? F of a divided by f of b. All right, if I take a is less than b, this thing should be getting larger. So this should be less than or equal to 1 to show that it's increasing, right? If I multiply both sides by f of b, I would have f of a is less than or equal to f of b, which is exactly what we're looking for. Okay, so I just want to consider this ratio and find that it's less than or equal to 1, which turns out to be not too bad to do. All right. Again, we can think of this as a sequence as well. So whether you're thinking of it as a sequence or just in the explicit definition of increasing, doesn't matter. It's all the same for this example. All right, so 2 to the a minus 1 divided by 2 to the a, that's f of a, divided by 2 to the b minus 1 divided by 2 to the b, that's f of b. Of course, when we divide by a fraction, that's the same as multiplying by the reciprocal. So this is 2 to the a minus 1 divided by 2 to the a, multiplied by 2 to the b divided by 2 to the b minus 1. And this works out pretty nicely because b is larger than a, and it's larger by k. So this is going to be equal to, now let's see here, these reduce, so we're left with 2 to the k, still have 2 to the a minus 1 divided by 2 to the b minus 1. From here, I can distribute the 2 to the k in. So I've got 2 to the k times 2 to the a, which is 2 to the a plus k. But b is 2 to the a plus k. Right? B is a plus k. B is not 2 to the a plus k. So 2 to the k, 2 to the a gives us 2 to the b, minus 2 to the k, divided by 2 to the b minus 1. And of course, this is less than 1, since 2 to the b minus 2 to the k would in fact be less than 2 to the b minus 1. Right? Our k value is greater than 0. So this is at least 2 to the first. So a number minus 2 is less than that same number minus 1. So we do have that the ratio is less than 1 and that the function capital F is increasing. Excellent. And that's all that we were looking to show. So our function does in fact satisfy this. And I thought it was an interesting thing to consider because, again, it's this infinite sequence, or this, right, we can have an infinite number of possible discrete values for our discrete random variable. So it should be something a little bit different than what you're seeing in other places, such as the textbook, which you should be reading in this course with me. All right, so that's all that I have for this video, and we've got one more video to consider that should also be relatively short. Hopefully these past ones have been. So I'll see you guys soon back here in the workshop.